Hello friends, you are watching ISC Mathematics. Please like and subscribe my channel ISC Mathematics. In the previous video, I had given the complete explanation of the chapter binary operations. In this video, we are going to solve the exercise based on this chapter. Okay, so let us begin the exercise. See here question 1. So that the addition and multiplication are binary operations on the set E of positive even integers. So in question number 1, we are given E is equal to set of positive even integers. We have to show that addition and multiplication are binary but division is not binary. We have to show that addition and multiplication are binary but division is not binary. Okay, we are given set E, which is a set of positive even integers. So suppose binary operation, we know that binary operation is a function. Okay, if binary operation is defined on set E, then we can consider a function f from E cross E to E. That means the domain is E cross E, okay, and the codomain is E. So it is very clear that if you take any two numbers from E cross E, okay, so let A comma B belongs to E cross E, okay, then we know that A plus B okay, A operation A asterisk B is given by A plus B. Okay, now we know that A plus B, that means the sum of two even integers will always be even only. Clear? So we can write that A plus B is even for all A comma B belongs to E cross E. Yes or no? And therefore the binary operation addition is even. Why? Because the sum of two even integers is an even integer, and similarly the product of and we can consider another operation A order B is equal to A cross B. Okay, this is also even. Why? Because if you multiply any two even numbers, the product of two even numbers will always be even only. You can give one example, you can consider any example. Suppose for 2 comma 4 belongs to E cross E, we know that 2 plus 4 is equal to 6 is even, and this will be true for any two even numbers. Yes or no? Similarly, for 2 comma 4 belongs to E cross E, 2 multiplied by 4 is equal to 8 is also even. Clear? So from the two examples now you can understand that addition of two even integers is even number, and therefore this addition operation is binary on set E. Similarly, multiplication of two even numbers is always even, and therefore multiplication is also binary, and therefore we will write down that addition and multiplication are binary on set E. Clear? Note down. Okay, now let us solve the next question. In the next question number 2, we are given set A containing elements A, B and C. Okay, and power set of set A. We know that what is power set of set A? It is a set containing all the subsets of A. And we know that there will be 2 raised to 3, that means there will be total 8, yes, there will be 2 raised to 3, so 8 subsets will be there. Clear? Okay, now we have to show that union is binary on P of A. Okay, so now let us prove. Let A and B belongs to P of A. Yes or no? Now, where A and B are here, where A and B are any two subsets of set A. Clear? Okay, now if you take the union and therefore A union B, yes or no? A union B, if you take, obviously this will be a subset of P of A. Clear? It means if you take the union of any two subsets of set A, then the union of the two subsets will belong to the power set A. It is very clear. Okay, and therefore we can write down that union, let me write down over here. Okay, this fact can be understood with the help of example. For giving example, let me write down the subsets of these sets, all subsets, or let us make a power set A for the given set A. So empty set, we can write down 8 elements of P of A quickly. Okay, so these are the 8 subsets and P of A contains all these subsets. Okay, now consider any two subsets. Suppose we have taken A and this 2. Okay, so if you take the union of these two, obviously will be equal to ABC, which is, okay, which is a subset of P of A only, or it belongs to P of A, yes or no, this last element, clear? And therefore, so similar way you can take the union of any two sets, even empty set and this last subset. Okay, so you will find that the union is A comma B comma C, which belongs to P of A. So if you take the union of any two subsets from P of A, the answer will belong to P of A only, and therefore it is binary, and therefore we will write down, therefore union is binary on P of A. Clear? Note down please. Okay, now question number 3. Set A containing three elements x, y and z is given. Okay, you are given a composition table defining the operation, binary operation asterisk x, z, y, z, y, x, y, x, z. Okay, this composition table is given in the question. We have to find out the certain values x asterisk x. So we know how to find the values x asterisk x. This answer will be x only. Okay, similarly you can find out the other answers. X asterisk y we have to find out. Then yx zx yy zy xz yy zy and xz. Now let us write down the answers. This is very easy question. X y. Okay, what will be the answer? Sorry, here x y answer will be z. Y x answer will be z. Then we have to find zx. So zx answer will be y. Then we have to find yy answer will be y only. Okay, and then we have to find zy answer will be x. And finally xz answer will be y. So quite easy question. From the table you have to answer this. Okay, now with this let us see the next question. Addition and multiplication are commutative and associative on the set B of odd integers, but subtraction is neither commutative nor associative. I think addition is not well defined on the set of odd integers. Yes or no? Addition is not well defined on the set of odd integers. If we take 4 to be the set of odd integers, okay, then addition of two odd integers will not be odd. For example, 1, 3 is 4 is not odd. Yes or no? It does not belong to set O, and therefore addition is not well defined on the set of odd integers. Clear? So we will not explain the commutativity, we will not discuss for this. However, addition operation is commutative only always, okay, for all real numbers. But as far as this chapter is considered binary operation, so here addition is not binary, we will say, because the sum of two odds is not always an odd number. Yes or no? Clear? Because it will always give you the even number. So this addition is not binary. However, multiplication is binary, because multiplication, okay, let us check the multiplication. 1 3s are 3, 1 5s are 5, 3 5s are 15. So we are getting odd numbers. Yes or no? So multiplication can be explained like this. Okay, so here I will write down that addition is not binary. You have understood. Now let us check the multiplication. Okay, for all AB belongs to set O, A multiplied by B is equal to B multiplied by A. Yes or no? And therefore multiplication is commutative. Here similarly, for all A, B and C belongs to O, A multiplied by B multiplied by C is equal to A multiplied by B multiplied by C, we know. Okay, and therefore multiplication is associative. Okay, because this both equal A multiplied by B multiplied by C only. So answer will remain same in both the cases. So commutativity and associativity hold for multiplication on set O of odd integers, but addition is not binary. Therefore we are not explaining here commutativity and associativity. Please note down quickly. Okay, in this question, subtraction is neither commutative nor associative. We have to show this. We have to prove even in question number 4 that subtraction is neither commutative nor associative. Okay, let us explain this over here. Let us discuss for the subtraction we will discuss commutativity. Obviously for 5 and 3 belongs to O, 5 minus 3 is not equal to 3 minus 5, and therefore subtraction is not commutative. Now associativity. Okay, for 5, 3 and 1 belongs to O. Okay, 5 minus 3 minus 1 equal to 5 minus 3 is 2, 2 minus 1 equal to 1, and 5 minus 3 minus 1, 5 minus 2, which is equal to 3, and therefore 1 is not equal to 3. It is very clear, and therefore associativity also does not hold, and therefore we will write down over here that subtraction is not associative. Therefore subtraction is not associative. Okay, on set O. Okay, now next question, that is question number 5. On the set of integers is given Z. Okay, a binary operation is defined by A asterisk B is equal to A plus B plus 1. Okay, where plus is the ordinary addition. Associative property holds we have to find the identity element, and inverse also we have to show that inverse is minus a minus 2. Okay, 2002 ISC board question. It was asked in 2002. Okay, now the very first property which we have to prove is associativity. So associativity, let us prove this property. Let A, B and C belongs to Z such that A asterisk B asterisk C. Now we will find out this A asterisk B asterisk C is equal to, let us put the value. A asterisk B is well defined, A plus B plus 1, A plus B plus 1 asterisk C. Okay, now it is important. Now in this expression, this represents the left side value with respect to this asterisk symbol. Left value represents A and right value represents B. So remember that you have to put the two values in this formula. For A we will put this bracket and for B we will put C. So this will become like this: A plus B plus 1 plus C plus 1. And now when you simplify, you will get A plus B plus C plus 2. Now let us take right hand side A asterisk B asterisk C. Okay, now A asterisk B asterisk C we can find out by using this formula: B plus C plus 1, B plus C plus 1. And further, in the same manner, in this formula we will put these two values. For A we will put A only, for B we will put this bracket. So it will become A plus B plus C plus 1 plus 1, which is equal to A plus B plus C plus 2, and therefore LHS is equal to RHS, and therefore operation asterisk is associative on Z. So far we have proved associativity. Now we have to find the inverse element. Now recall the definition. Okay, let E belongs to Z such that A asterisk E is equal to A is equal to E asterisk A. Okay, and therefore A asterisk E is equals to A. Now use the formula for A asterisk E, A plus E plus 1, and therefore A plus E plus 1 is equal to A, and therefore E is equal to minus 1. Okay, so value of E is minus 1. Now finally we will find out the inverse element. Actually it is already given that the inverse is this in your textbook. So we have to just show that the inverse is minus A minus 2. Okay, so let us do this on the left hand side. I hope you have taken down this. Okay, now let B belongs to, okay, B are there only, no need to write. A asterisk B is equal to E is equal to B asterisk A. This is the definition, okay, for the inverse, and therefore A asterisk B is equal to E. Therefore A plus B plus 1 is equal to minus 1, because value of E is minus 1. From 1 we can write down from 1, and therefore A plus B is equal to minus 2. Remember that B is the inverse element of A. So B is equals to minus 2 minus A, or B is equal to minus A minus 2. Hence prove that the inverse element of A is minus A minus 2. note down quickly. Okay, now let us solve the next question, question number 6. Okay, O dot, a binary operation, O dot is defined on Q. Q is a set of all rational numbers other than 1. Other than 1 in this case. Okay. Now the operation is given A O dot B is given by A plus B minus AB. We have to show that this binary operation is commutative, associative, and 0 is identity element. So here we have to show two things, commutativity and associativity. These two things we have to show. So let us first show that this is commutative. Okay, so for that LHS we will take A O dot B is equal to A plus B minus AB. Now let us reverse. So B plus A minus BA, this is equals to B O dot A, and which is equal to RHS. So LHS is equal to RHS is 2. Therefore O dot is commutative. Now we will prove associativity. Let A, B and C belongs to Q minus 1, or it is Q other than 1. Q is already explained as set of rational numbers other than 1 in this particular case. Okay, so A plus B plus C is equal to A plus B, we have formula A plus B minus AB plus C. Okay, is equal to now we will again okay, it was a mistake. Rather than writing A plus C, we will write A O dot O dot. Okay, so here O dot will come because O dot is defined as A plus B minus AB. Okay, now again, if you want to find value of this operation, then again in the given formula for A, we will put this bracket will be substituted for A, and B will be replaced with C. Clear? So let us do that. Therefore A plus B minus AB plus C minus A plus B minus AB into C, and now we will simplify. So we will get A plus B minus AB plus C minus A minus B. Okay, it is C will be multiplied inside, so minus AC minus BC plus ABC. Clear? So now further writing in A plus B plus C minus AB minus BC minus AC plus ABC. This is the left hand side, LHS. Now we will take RHS and we will prove the same. Okay. So now RHS we will do on this side. Okay, in RHS we have to prove that A O dot B O dot C is equal to A O dot. Okay, B O dot C will be given by B plus C minus BC. Okay, using the formula. Now again we will put in the formula for A only and for B this whole bracket. So A plus B minus A B. Yes or no? Now let us simplify A plus B plus C minus A plus B plus C minus BC minus AB minus AC plus ABC. Okay, which is equal to A plus B plus C minus AB minus BC minus AC plus ABC number 2. Now observe the two results, both are equal only, and therefore LHS is equal to RHS, and therefore associativity holds for the given operation in Q. Clear? Okay, so I write down over here. Therefore, O dot is associative. Okay, now identity element A asterisk E is equal to A is equal to E asterisk A. The first step is a common step to find the identity element in each question. So remember this. This is a definition. Therefore, A asterisk E is equal to A. Now put the formula for A asterisk E. A plus E minus AE is equal to A. Okay, from the two terms E we can take common, so E 1 minus A is equal to 0. Therefore E is equal to 0 upon 1 minus A for all A not equal to 1. Therefore E is 0, and therefore the identity element is 0 that we had to prove, and we have proved. Clear? Please note down. I hope you are getting this very easy chapter. Only thing is you need to understand the definition of binary operation first of all. Okay, if you have understood the definition of binary operation very well, then you can understand the other things. After you have understood in a proper manner the definition, then go through the definitions of identity element and inverse element. Okay, and commutative, associativity and commutativity is quite easy to prove, that you have been proving since the lower classes. Okay, now let us solve the next question. Okay, question number 7 is quite easy. You have to show that addition defined on the set of integers holds associativity, commutativity, it has um, identity element, and it also has a additive inverse. So it is quite easy because addition we have already seen while explaining the definition and all. After that I had explained you all the properties. At that time we have already taken the example of addition on z set of integers. Okay, so you just, if in case any confusion, just refer that video, you will get. Okay, however it is easy, I don't think that you need to refer that again, you can solve yourself. Okay, question number 8. Okay, question number 8, it is given that show that the set n of natural numbers with respect to the addition as the binary operation has identity. Now in the question it is given that set of natural number n, this is question number 8, set of natural numbers is given. Now addition is binary. Okay, addition is binary, we know, because the sum of two natural numbers will be a natural number, because when any binary operation f is defined on n, it means it is a function from n cross n to n. Okay, so if addition you are taking, then the sum of two natural numbers is a natural number, so it belongs to codomain. Yes or no? And therefore it is binary. But in this question they have given that identity element exists, but identity element does not exist for set of natural numbers when binary operation is defined on n. How? See, because for a and b belongs to n, or rather than taking a and b, let us take two examples. 2, 3 belongs to n, or we are explaining the identity. Okay, so only one element we will take. For 2 belongs to n, what is the definition? A asterisk e is equals to a is equals to e is asterisk a, and therefore a asterisk e is equals to a. Now a value of a is 2 here, so 2, and addition we are taking, so 2 plus e is equal to 2, so e is equal to 0, but we know that 0 does not belong to n. Yes or no? Then how it is possible that addition is binary on n? Okay, identity element exists. Okay, so there is some mistake, because identity element for the addition operation on n will not exist. Is it clear? However, okay, since identity element does not exist, obviously inverse will also not exist. Clear? So identity element, there is some mistake in the question they have given that it has identity element, but I have just explained you that for the binary operation addition on set n, it does not have any identity element, and hence inverse also does not exist. Okay, question number 9. Prove that in the set 1, minus 1, let us name the set to be set A. It has two elements. Now multiplication is binary operation and all the 5 properties are satisfied. Okay, let us discuss multiplication here. A asterisk b is equal to a multiplied by b. Binary operation is multiplication. Clear? So now here in your textbook it is given that explain all the 5 properties. Actually there are 4 properties: commutativity, associativity, additive, identity element, and inverse element. Clear? What is the 5th property according to your textbook is the closure property. But while explaining the definition, I explained you that the binary operation holds closure property. That means what? if the given operation is binary or binary operation is well defined on a particular set, it means it always holds a closure property. I mean to say what? If we are taking a binary operation denoted by f, so obviously it is a function f from a cross a to a. Clear? So if we are taking any two elements from set A, then on operating, the whatever answer comes, that answer must come in set A only. Then only it is binary. Okay, by definition only. So obviously it will hold closure property. Clear? So that is the closure property. Here obviously it is very clear that if you take any two elements from A cross A, we know that there will be four elements in A cross A. 1 1 1 minus 1 minus 1 1 and minus 1 minus 1. Four elements will be there, and if you multiply, the answer will be in A only. So closure property holds. It means binary operation is well defined on set A, we can say. Clear? So I will write down over here number 1. Okay, since for all A comma B belongs to set A, A multiplied by B belongs to set A, and therefore asterisk or multiplication is binary on set A, or as per your textbook you can write down that multiplication holds closure property in set A. Clear? Now number 2, commutativity. Obviously the multiplication is commutative. Okay, so for all A comma B belongs to set A, A multiplied B will be equal to B multiplied by A only. Okay, so you can check these all the four pairs, one multiplied by 1, and on reversing you will get same answer only. Here also on reversing you will get minus 1 only, so it is very easy to understand. Okay, and therefore asterisk or multiplication is commutative. Then associativity. Okay, associativity also will hold. Okay, because for any elements A, B, C, for all A, B, C belongs to set A multiplied by B multiplied by C is equal to A multiplied by B multiplied by C. Okay, here you can take the elements like 1, 1, minus 1 like that. Okay, two same element and one different, because there are only two elements given in the set. Okay, and therefore you can explain by giving example A, B, C, 1, 1 minus 1, or 1 minus 1 minus 1, or 1 minus 1, 1, anyway you can take and explain. Clear? So, and therefore we will write down that multiplication is associative. Clear? Okay, now let us see the additive inverse. Now before that, before finding the inverse, identity element. Identity element. Okay, so now let E belongs to set A such that A asterisk E is equal to E so 1 is the identity element, and finally we will find out the, obviously this must belong to set A only and 1 belongs to set A. Okay, now additive inverse number 5, this was number 4. Additive inverse, okay, let B belongs to set A, let A and B belongs to set A such that A asterisk B is equal to E is equal to B asterisk A. Therefore, A asterisk B is equal to E. A multiplied by B is equal to E is 1. Therefore, B is equal to 1 by A. A is not equal to 0. So, for the two elements, you can find out the inverses. For A is equal to 1, B is equal to 1, and for A is equal to minus 1, B will be equal to minus 1. Okay, so additive inverse also we got. Please note down. Okay, now let us solve question number 10. Okay, in this question you are given Q is equal to set of all non-zero rational numbers. Okay, and a binary operation asterisk is defined by A asterisk B is equals to AB upon 2. Okay, 5 properties hold in Q. Again, the 5 properties which we discussed in the previous question, we have to show in this question also. Let us take the first one. Okay, and check whether A asterisk B is binary or not. Okay, so it is quite easy. For A and B belongs to Q, A asterisk B is equal to AB by 2 belongs to Q only. Yes or no? Or if you take, if we consider this as ordered pair, so A comma B belongs to Q comma Q, A asterisk B is equal to AB by 2 obviously will be a non-zero rational number only, because A and B are non-zero. So product of AB divided by 2 will be a rational number always, because it will be a fraction only, whether positive or negative, and therefore we can say that asterisk is binary on Q, or it holds the closure property in Q. Okay, now second one, commutativity. Okay, LHS is equals to A asterisk B is equals to AB by 2 is equals to BA by 2 is equals to B asterisk A is equal to RHS, and therefore asterisk is commutative. Here, just go through the commutativity, it is very easy. And then associativity. LHS A asterisk B asterisk C is equals to AB by 2 asterisk C is equal to, let us write down the remaining steps on the left hand side. Before that we will just go through the first one. Since for any two numbers A and B in Q, AB by 2 will also belong to Q, and therefore this is binary. AB by 2 or BA by 2 will give you the same answer in Q, and therefore it is commutative. Now associativity we are checking. Okay, simply again, now this is important. We have to put these values in this formula. So for A we will put this bracket, and for B we will put C. So this will be like this: AB by 2 into C upon 2, which is equal to ABC upon 4. Clear? Okay, now let us take the RHS. So A asterisk B asterisk C is equals to E asterisk BC by 2 is equals to A into BC by 2 by 2 is equal to ABC by 4, and therefore from these two results we can say that LHS is equal to RHS, and therefore associativity holds. Okay, and therefore from 1 and 2 we can say that A asterisk B asterisk C is equals to A asterisk B C, and therefore this operation is associative. Okay, now identity element. Let E belongs to Q, therefore A asterisk B is equals to A is equals to E asterisk A, therefore A asterisk E is equals to A, therefore E by 2 is equals to A, therefore E is equal to 2. We got the identity element to be equal to 2. Okay, now finally we will find out the inverse element. I hope you have taken down these steps. Okay, now number 5, inverse element. Let A and B belongs to Q such that A asterisk B is equals to E is equals to B asterisk A, therefore A asterisk B is equals to E, therefore AB by 2 is equals to 2, therefore B is equals to 4 by A, or A not equal to 0. This is the inverse element. So quite easy this question was. Okay, now let us solve question number 11. You have understood this question, I think. Yes or no? So far, I don't think that there will be any difficulty in solving this exercise. If you have gone through the theoretical part, then it will be easy for you to understand these questions. Let us solve question number 11. Okay, a binary operation asterisk is defined on n. N is a set of natural numbers. It is defined by a asterisk b is equal to a raised to b for all a b belongs to n. Okay, we have to show that it is neither commutative nor associative. Okay, let us prove what commutativity. Let us check the commutativity. Okay, let a and b belongs to n such that a asterisk b is equal to a raised to b. Okay, and obviously this is not equal to okay here such that a is not equal to b in this particular case. Yes or no? So a asterisk b is equal to a raised to b is not equal to b raised to a and therefore is not equal to b asterisk a. Therefore a asterisk b is not equal to b asterisk a and therefore given operation is not commutative. Now second part, associativity. Let a comma b comma c belongs to n. Okay, such that a is not equal to b is not equal to c. Okay. Therefore a asterisk b asterisk c, or rather than writing a b c, I will write down all are not equal at a time. A b c are all not equal at a time. Okay, now a asterisk b asterisk c is equals to a raised to b asterisk c is equals to a will be equal to a raised to bc. Now a asterisk b asterisk c is equals to a asterisk b raised to c is equals to again a raised to b raised to c, and therefore from 1 and 2, because in the first we got a raised to bc and in the second result we got a raised to b raised to c, not equal. Okay, and therefore from 1 and 2 we can say that a asterisk b asterisk c is not equal to a asterisk b asterisk c. Okay, and therefore the given operation is not associative. Please note down. Okay, now next question. question number 12. You are given a binary operation defined by A asterisk B is equals to A for all and set A asterisk is defined on set A. Okay, where set A is a non-empty set containing more than two elements, two or more than two elements. It is given in the question. Okay, so and operation is defined by A asterisk B is equals to A. We have to show this that this is associative. Let us show that this is associative first. Associativity. Okay, so here we take three elements. Let A, B, C belongs to set A. Now A asterisk B asterisk C is equals to, now A asterisk B is A. Yes or no? Since A asterisk B is equals to A and finally will be A only. Okay, and RHS and A asterisk B asterisk C is equals to A asterisk B. Since B asterisk C will be equal to B by definition and finally will be equal to A, and therefore we can write from these two results that A asterisk B asterisk C is equals to A asterisk B asterisk C, and therefore the given operation is associative. Okay, now identity element you are told to find. Actually they have given that so that identity element does not exist. Okay, so let us do that. Okay, now A asterisk E is equal to A is equal to E asterisk A. Okay, we will write down the definition. Clear? So now therefore A asterisk E is equal to A implies A is equals to A. So E vanishes. Yes or no? And therefore we will write down that identity element does not exist. Here, okay. And the commutativity we have to check. Let us check the commutativity also. Okay, now A asterisk B is equal to A and B asterisk A is equals to B, and therefore LHS is not equal to RHS unless A and B are not equal. Because if A and B are equal, then for that particular case the commutativity will hold, but not for all the elements. For unequal elements it does not hold, and therefore this given operation is not commutative for all A not equal to B. Okay, you must mention this. So I hope just go through first associativity. The two sides LHS and RHS we have proved to be equal, and therefore associativity holds. Okay, identity element then we have checked. Okay, obviously E vanishes and therefore no identity element exists, and commutativity if you check for A and B not equal, LHS and RHS are different. Okay, and therefore commutativity does not hold for all A not equal to B. So today till question number 12 we have finished. Now very few questions are left. Okay, hardly 20-21 questions are more left in this exercise, and this chapter